Alright, so these are again rational functions, but there are three cases when it comes to horizontal asymptotes. We saw one of the other cases before. Let me just give you kind of three basic examples so you can see what the three cases are. Okay, so we'll use a similar example. So let's suppose you had, here's an example of case 1. Case 1 is when the denominator, the degree on the denominator is larger. So like x plus 1 over x squared plus 1. Okay, let's just do 3x squared plus 1. We'll make that, 3x squared plus 1. So in this case, basically the horizontal asymptotes occur as x goes to infinity. And this notation that I'm writing right here, that's the symbol, x arrow, and then that's the infinity symbol. So think of it this way. If you were to plug in infinity for x, you get infinity plus 1 over 3 infinity squareds plus 1. Infinity is so much bigger than 1 that the 1's don't even really matter there. So this is the same thing as infinity over 3 infinity squared. And if you were to, you can't really do this, infinity doesn't work like this, but I'm just using it as an analogy. If you were to cancel this infinity, infinity goes into itself once, and it goes into infinity squared infinity times. So this is 1 over 3 infinities. And if you were to put that in a calculator, 1 over an enormously large number, that's basically equal to 0. So case 1 is when the denominator has a larger degree, that's x squared, than the numerator, that's x to the 1. And in that case, your asymptote, your horizontal asymptote is 0. Case 2, we use a very similar example. Case 2 is when, suppose the top, instead of x plus 1, were x squared plus 1. Okay, if you followed the same process with infinity up there, you'd have this becoming infinity squared over 3 infinity squared. We don't care about the plus 1 because infinity is going to dominate that. It's so much larger. Infinity squared goes into itself once, and it goes into that once, so we're just left with 1 over 3. So case 2 is when these have the same degree, and in that case you take the ratio of these numbers, 1 over 3. Case 3 would be something like this. Case 3 would be something like x cubed plus 1 over 3x squared. This is not going to have a horizontal asymptote because it would turn out to be like this. Okay, 3 infinity squared. That will, infinity squared goes into that, infinity times that goes away. So it's an infinitely large number over 3. That's not a horizontal asymptote. You get something called an oblique asymptote. In order to find it, you would have to do long division, basically. And whatever you get when you do this long division, this thing up here, that's going to be what the asymptote is. Okay, those are not as commonly covered in Algebra 2. You see them more in pre-calculus. Alright, so first of all, let's decide if this is case 1 or case 2. So this is 2x squared over x squared. The degrees are the same, so that's a case 2. So that means our horizontal asymptote is just going to be the ratio of 2 over 1, okay, or 2. So horizontal asymptote will be y equals 2. That means the range is going to be y does not equal 2. Okay, so let's see if we can find that. And actually, let's just again do this kind of the long way, just to get the practice of graphing this if it were not multiple choice. So let's start by pulling out a 2 right here. If you do that, you'd have x squared plus 3x minus 4. That's going to factor to what multiplies to negative 4 adds to 3, x plus 4 times x minus 1. And then this bottom one, I believe, will factor to x plus 3 times x minus 2. So here's our new function. We have f of x. F of x is going to equal the following. Okay, it's going to equal 2 times x plus 4 over x minus 1. And whenever we're doing these problems, what I would recommend as a first step is to factor everything and identify all the stuff they're telling you to identify here. Discontinuity, asymptotes, and so on. And I'll show you how to find those. So we have on the bottom x plus 3 and then times x minus 2. If there was something we could cancel, if there was like an x plus 3 on the top and the bottom, that would be what's called a discontinuity. Basically your graph would just have a hole in it at that point. Okay, in this case there is no discontinuity. So our vertical asymptotes are going to be what makes this first one 0, which is negative 3, and the second one is made 0 by x equals 2. So let's start our graph right there. So we're going to have a vertical asymptote at negative 3, and that means we're also going to have a vertical asymptote at 2. So we should actually have 3 parts of the graph here. We should have something here, and something here. Basically something on every side of the asymptotes. Okay, those are our vertical asymptotes. We already said from before down here that our horizontal asymptote is y equals 2. So let's add that also. Actually, let me use different colors for these just so that you can see it a little bit better against the backdrop. So here's y equals 2. There's our asymptote. Okay, now and then here's the other thing that would be useful. It would be useful to know the x and y intercepts if there are any. Okay, so the x and y intercepts, how do you find those? Well, the x-intercepts you find by setting y equal to 0. So the x-intercept will be where y equals 0. So let's take this and set it equal to 0. And actually, here's the thing. I'm not even going to write the bottom because the bottom can never make a fraction 0. The only way that a fraction can be 0 is if the top equals 0. If the bottom is 0, you don't have 0. You have undefined. You can't do that. So what would make this 0? X equals -4 would make the top 0, and also x equals 1. So that means we're going to have zeros or x-intercepts at -4, which is right here, and at +1, which is right here. Okay, that was helpful because at least now we know some points on our graph. Okay, that was the x-intercepts. Let's see if there are any y-intercepts. And those occur when x equals 0. So if we plug in 0 here, we'd have 2 times 0 plus 4 is 4. I'm plugging it into these. 0 minus 1 is -1. And the bottom is going to be 0 plus 3, which is 3. And 0 minus 2 is -2. So the top is going to be -8, and the bottom is -6, and that becomes 4/3. So we have a point at 0, 4/3, or 1 1/3. That's about right here. Okay, so question is, how is this graph going to look from there? Well, let's just plug in a few more points to get a sense. And you can see kind of roughly what the shape is going to be, but we want to know a little bit more. So here's the thing. We now know what the middle part is going to do. It has to come down here. There's no other way that it can respect that asymptote. And it's not going to swing around, but if you want to prove that to yourself, let's just make a brief table of values and plug in some points. Okay, so we have 2 times, what was this function? X plus 4 times x minus 1, and that's all going to go over x plus 3 times x minus 2. So we want to pick a point that is to the left of that, to the left of x equals 0. Let's just pick -1. Okay, when we plug in -1, we're going to get, should have left a little bit more space there. We're going to get this. When we plug in -1, we'll get y equals 2 times -1 plus 4 is 3. -1 minus 1 is -2, and the bottom is going to be 2 times -3. So what does that become? -12 over -6, which is +2. So -1, +2 is the y. Now you might say, I thought +2 was an asymptote, and you're right, it is. But graphs can cross the horizontal asymptote in the middle of the graph. So in this region right here, in this zone, we haven't gone out to infinity. Remember that horizontal asymptotes are where does the graph go as x goes to infinity. We're not at infinity in this purple line that I'm drawing. We're at right in the middle of the graph. So it is possible to cross the horizontal. It's never possible to cross the vertical though. Okay, and then let's just get some points in the other region of the graph. So over here, we know that's x equals 2, so let's get x equals 3 and 4, just to see where those go, and we'll just speed up the math here. So the top is going to be -28, and the bottom is going to be 6 times 1, which is 6. So that's roughly -4 and -4.7 approximately. So 3 -4.7 is about right down here somewhere. And then let's get x equals 4. So 16 times 3 is going to be 48. I'm just doing some mental math here. And then 7 times 2 is 14. That's roughly 3. What is that? 3, not quite 3.5. So maybe somewhere around 3.4. Let's say roughly. Okay, 3.4, and that's +3.4. So that's going to put us somewhere up here. Let's say. About 3.4. So you can see how this graph is going to go. It's going to go down this way, and it's going to go up this way. Now, here's the thing. You might want to look at this picture to kind of tell how it's going to look. We actually, hold on. I think I should say I made a mistake in the math right there, because that picture wouldn't make sense. If you plug in 3 on the top, 7 times, oh no, that's a +28. That's why it's not working. Okay, so yeah, I was going to say that's a sign that the graph shouldn't be crossing like you saw right there. So that's going to be a +4.7, which is somewhere up here. Now that picture makes sense. Now it's going down this way, and oops, let me erase all this stuff right here. It's going down this way, so it's approaching the horizontal asymptote, and then it's going up this way, so it goes towards the vertical. Okay, the last one is points to the left of -3. That's over here. And we already have one of them. Okay, let's just plug in one more. So let's plug in -5. If you were to plug in -5 up here, let me make another tip. If you plug in -5 to this, you'd have 2 times -1, which is -2, times -6 is 12. I'm just kind of mentally plugging -5 in right here to the top. And then the bottom, if you plug in -5 to the bottom, -5 plus 3 is -2, times -7 is 14. So that's roughly 0.8 or 0.9. So -5 comma 0.9 puts us about right here. So you can see how it's going to go. It has to go down here and it has to go off like that. And the only one that works for, again, this was multiple choice, so I just want to show you how to do it if we're not multiple choice. The only one that it works for is C. Okay, this one is a case 3. So just to remind you, case 3 from back here is when the top has a larger denominator or larger degree than the bottom. So this is not going to have a horizontal asymptote. Let's always start by factoring. So if we factor an x out of the first top right there, we'd have this. And if we factor a -4 from the bottom, we'd have x minus 4. I factored a -4 because that's negative right there. Okay, the vertical asymptote is what makes the denominator 0, and that's x equals 4. That means the domain is x cannot be 4. So we're looking for a vertical asymptote of 4. The horizontal asymptote, remember, it doesn't have one, so there should not be a horizontal asymptote here. And so that means pretty much all of these have horizontal asymptotes except for D. But let's just do a couple more just to double check. Okay, so there's no horizontal asymptote. The zeros would be when the top equals 0. So x equals 0 and x equals 3 would make would be the x-intercepts. That's what makes y equals 0. So it's going to be D because D is the only one that doesn't have a horizontal asymptote. Let's double check. So there should be a 0 at x equals 0, and there is. Should be another 0 at x equals 3, and there is. There should be a vertical asymptote at x equals 4, and you can see it's right there. Okay, and then from there, to get the other shape of the graph, you can really just plug in points. You see how it's kind of dipping right here, but it's, if you want to see why does it turn around, you can plug in a point in between 3 and 4. Okay, and then I wouldn't worry as much about getting the way that horizontal asymptote looks, or I should say the oblique asymptote. If you do want to find it, though, here's how you would find it. You would do, our function is x squared minus 3x divided by -4x plus 16. So the way that you would find it, if you wanted to make it really accurate, is you would do this long division right here. And whatever you get, you're going to get some sort of line that you can see it's kind of approaching right here. It might go somewhere like that, but you usually are not responsible for knowing that in Algebra 2 at least. Okay, so the discontinuity is at 4 because that's where the asymptote occurs. And that's really all we need to do there, so it's option D. Okay, this final one is a case 1. That's when the degree of the numerator is smaller. So we can pull out a 2 from right here, and we're left with x squared plus 2x minus 3. And then we could even factor that more. So that x squared plus 2x minus 3 factors to x plus 3 times x minus 1. So x plus 3 times x minus 1. Okay, here's the thing. There's actually only one vertical asymptote here, and that's x equals 1. That's going to come from here. Why is x equals, or why does that x plus 3 not give us a vertical asymptote? Because there's also an x plus 3 on the top. So there's a discontinuity there at x equals -3. That's a discontinuity, but it's not an asymptote. It's really going to give you, essentially, it's called a point discontinuity. There's just going to be a hole in the middle of the graph. So we should look for a vertical asymptote at x equals 1 and a hole at -3. So this one might be an option because that only has one vertical asymptote, but it has both of those discontinuities. Both vertical asymptotes and holes are called discontinuities, but they're not both asymptotes. Only ones that do not cancel with the top. So like x minus 1 in that problem did not cancel with the top. This one is done because there is a vertical asymptote. That one's wrong. And this one is wrong too. So the only one that works is this because it has a vertical asymptote at x equals 1. And you can see it has this little hole in the graph right there at -3 because -3 canceled with the top and the bottom. And the horizontal asymptote in this case, in a case 1 example, remember this is like infinity over infinity squared. The bottom is a huge number, so something over a huge number is just 0. So y equals 0, and you can see that right here. It's a little bit hard to make out, but it's going towards 0. So that's, again, to get those other points, you can plug them into a table of values like we've done in the other ones. All right, number 24, 25, and 26. These are on variation problems, and actually we'll pick this up in the next video on section 8.5.